All right, so welcome everybody. We're going to go over ray tracing and global illumination today. How many people are ready to give their state-of-the-art talk? Got 2 people? Okay. So I think what I'd like to do is push those off to Wednesday so that everybody has a chance to, I'd rather it be more of a, everybody reports their findings. So that'll give you an extra day to submit your proposal online, which is really what is due is the paper part. But if you haven't got the paper part done, then the presentation part is not ready. So, right. Well, some people start out that way, but if you still need to spend time collecting your thoughts, I guess that's the main idea there. So, so I think we'll go ahead and do that instead. So Wednesday we will do the presentations. All right. Okay. Let's see here. Okay. So today I wanted to get us started on ray tracing and global illumination. Let me just make sure I've saved my work here. Everybody remember what we talked about last time? Just by way of review so we don't forget from week to week what's going on.
Oh, yeah.
So part of what we did was, and I'll just zoom on by here, we were talking about the OpenGL pipeline, and we kind of looked at all the different things we have studied so far. So information, different, what all computer graphics topics there are to even study, game development, mathematical foundations, how OpenGL works, the first perspective. Last time we did second perspective, we talked about the Reyes architecture, which is one of the big rasterization algorithms out there. And then we started talking about physically based rendering and the rendering equation. So kind of talking about the science of how light reflects and how we calculate how much light is reflected. Those are things that are used in ray tracing and global illumination. So going on for the future, right? We're focused on what's state of the art for our applications, and just make sure that whatever you have chosen as state of the art is something that you're featuring in your program. So you don't want to talk about a topic that's, say, unrelated. So just as a reminder. So for example, if I was writing a video game and I wanted to use ray tracing, then that would be a great place to talk about ray tracing, what's state of the art right now, and knowing that I'm going to use ray tracing in my program. Okay. So this is a great way to kind of get the technical stuff out of the way. And so anyways, on the pipeline, we're going to be talking about ray tracing, global illumination, starting that today. All right. So I'm going to talk to you about the last 3 homework assignments that are coming up, and then we'll talk about homework 5 as well. But then we're going to start getting into more advanced things like some more NPR, textures, procedural generation, lights and shadows, and so on. Okay, so basically we were talking about the last component, really. How does OpenGL basically handle all the fragments that we give it? So we've given it data for the vertex shader, given it data for fragment shader, and now we'd like to be able to apply different operations to it. By far the most important ones out of all of these, there's, we have 6 of them here, but 3 of them are really the most important ones that we should remember something about. Stencil test, depth test, and alpha blending. Those are the kind of 3 that we should pay attention to. All right. So just, if you're studying this, we want to spend some time thinking about what's the stencil test used for, depth test, and alpha blending, because those are some of the most valuable tools. Scissor test is super easy, but you don't use it all that often unless you're implementing GUI widgets or something on the screen. All right. Okay, so yeah, so stencil test, for instance, we can use it for shadows, we can use it for reflection. I did actually see a really good demo on stencil shadows online. I don't remember if I have it still in my there was a WebGL demo that I saw. Let's see here. Maybe it was the Josh Beam website. Let's take a look. Yep, not that one. You either wrote an article or the, yeah, there's that. Where is it? Not this one. Well, this will show you how to do it. I should have saved it. I'll have to find it, and I'll put it on the Discord channel. But the it was an actual web application. You actually see what it's doing. Unless I can find an image of it online, since I remember what it looks like. It's known pretty much for the, you get sharp shadows. It tends to be a bit CPU intensive. But the idea here is that you can just do in a few passes, you basically project all of the objects with the light source, and you can project them, and they can be projected kind of to infinity. And then you render the back faces and you render the front faces. Anybody remember what a back face is? What's a back face?
The back side of the polygon.
Back side of the polygon. Okay, so if you're drawing a box, the back sides are all the faces that are pointing away from you, and the front sides are all the ones that are pointing towards you. All right. Let's see here. Let's see if this demo has. Lots of people have. You can find some of the stuff. Although stencil shadowing is harder to do. Most people like to focus on, oh, it might be this one. Most people like to focus on, yep. Like to focus on shadow mapping because it's far easier to do that with. This guy still have his, oh, we're getting close. Functional.
There was a mention of a video in that comment. I might do that.
Yeah, let's take a look at the video. Case. Okay, so that's just a demo, kind of showing it working. But there was a better one. I wonder if you can look in the history. Search stencil. Here we go. All right. This is the Stencil Shadow demo that I saw. It's pretty good. And what you can do is we can show the wireframe. And so you can see how we take the light source and we basically project the geometry. So we use the start, you can use the original vertex position, and then you basically calculate the vector from the vertex to the light. And then that you then just project your polygons basically just infinitely away. And so if you have an edge, you basically can project a quadrilateral plane in that direction. And then what you do, let me minimize that real quick, is your volumes, as you go in and out of the volumes, that allows you to decide whether or not it's in shadow or not. So you basically run this path. You run two passes. One draws back faces, one draws the front faces. And one of the quick ways here is it's called the Z-fail algorithm. And this is kind of funny, but this actually just came out of patent protection. So this was a big deal back in the 90s or late 90s in 2000. Creative Labs basically patented this this technique, and then John Carmack identified it on his own. So because he published the details, it's called Carmacks Reverse, even though he wasn't the guy. He was a, I guess you call, co-inventor. But so what ended up happening is he decided to strike a deal with Creative, and that's why they added EAX to their games for free. They didn't want to have some kind of money struggle going on. So in order to kind of provide a good experience for players, he said, okay, fine, we'll put EAX in the game and we'll use our shadow algorithm. And so that's kind of a little deal that he struck behind the scenes so you could use the algorithm. So there was a let's see here, a post that he has sent to Mark Kilgard, and Mark Kilgard's kind of famous for the OpenGL utility toolkit. When he used to work at Silicon Graphics, he works at NVIDIA now, I think, or he used to work at NVIDIA for a long time. And let's take a look at this. He was kind of, you can kind of see the thought process behind. Nope, that's not it. The thought process behind the shadow volumes. I'm looking for the John Carmack on look for that article real quick. There we go. Okay, so this is like an email, but what I like about this email is he summarizes what's happening. So you're like draw back sides, and then you increment the stencil and the depth buffer, right? And so he kind of goes through this whole process, and then basically it's two steps. So you draw the back sides, and you don't do anything with the depth pass, and then you increment when the depth fails. So you're running the shadow maps, and then you can draw the front sides of the shadow volumes, and then you do nothing with the depth pass, and you decrement with the depth fail. So if the depth fails, then you basically have them canceling each other out. And so you don't have to. He was using some fancy algorithms before to try and solve this problem, but it's actually a very simple algorithm that involves drawing the back sides and the front sides of the shadow volumes. So not the objects themselves. So when you look at a demo like this, what you're doing is you're drawing the front side and the back sides of the shadow volume. So you go in and you go out, you go in and out. And generally the other algorithm is pretty straightforward, except that you have to handle the case of what if you're inside the shadow volume, which could happen because if something's casting a shadow and you're inside, you need to be able to handle that offset. Okay, so this was a way to kind of handle that situation. All right, so let's look at the volume. So over here, even when you're generating the shadow volumes too, you can just use the back sides of the 3D model that you're generating. You don't need the front sides, obviously. So although if you do that, then you get a little bit more overdraw, but there's, you could definitely pick which ones you want. So the Z-pass algorithm is a little bit different than the Z-fail algorithm, and you'll notice the Z-fail is probably a little bit better for getting those geometry where you got hollow areas, right? Because you wouldn't like the teapot, for instance, if you ever looked at the 3D model, you notice there's a gap between the lid and the actual body of the teapot. So if you were to disable backface rendering, then technically you would see straight through the teapot because the back sides don't get drawn, and hence, you know, you have an issue there. Okay, so just one particular issue. All right, and I think if I back up, you can see kind of a projection of the teapot, right? So if I were to move the light around, you'll see that this projection moves. So you can basically just say, just project the light by 1,000 or 100 or whatever the case you want it to be, and then you render those polygons. Okay. So that's some more details on the shadow volume method. Okay, and then a reflection is pretty easy. You just mirror the image around the plane that you're going to draw the reflection on, and then you render it backwards. So you just flip everything to the other side of the plane and render it. And you can use the stencil then to kind of shadow or shade. So if it's like a red mirror, you can basically shade the or texture map the reflection, the appropriate color. Because if you were to, you know, if you had a red tinted glasses or something and you saw your reflection in it, you would not look, you would look red. All right. And speaking of this, it was actually reminding me, I was looking at another paper about, well, I don't know if it was a paper, it could have been some slides about transparency, right? Because, you know, shadows, if you were to say get some film gel, so you may have played with some kind of film gel before, it's just kind of tinted gel. And so if you were to hover that, put a light source on one side, the shadow is actually going to be tinted. And so you get a red shadow. If you had some red film gel, you shine a light through it, you're going to get a red shadow. But that's different than if you've ever, you know, had some of that fine, it's this type of fabric. It's got little tiny holes inside of it. So it's like a mesh type of fabric. And so if you shine a light straight through there, then you're not going to get a colored shadow. It's because you still have white light coming through. So you end up getting gray shadows instead. But transparency is one of those, it's basically one of those problems that are still not solved yet. It's a very complicated problem to solve. All right. So there's more to come. There's more to do with reflections, but that's some of the basic things you do with the stencil test. And then depth test is going to be good for shadow mapping, which we'll talk at some point later in the course. Okay. And we'll talk more about alpha blending as well when we get into texture maps. Okay. So I'm going to get rid of that. Okay. So that was kind of a review from last time, the OpenGL pipeline. Let me minimize that so it's puts in the background. All right. So, so now we want to kind of move ahead to ray tracing. So we talked a lot about rasterization in the course, and now we're going to talk about ray tracing. And more specifically, we're going to kind of get into global illumination. So, and we're going to talk about the homeworks. Okay, so we'll talk about homework 5. I moved the due date up to next Sunday, so you can do another 1-hour game jam project. But I would say if you have not, I would probably take a game you've already done this semester and make it better. Okay, and what I mean by make it better is find some ways of developing it out. All right, so for example, I was looking up, there's this book called, it's like these about game lenses, all right, and by Jesse Schnell, and this is a book I'm going to cover in the next course, next semester, on game development and design to some degree. But there's a, let me find who I'm following. Hopefully this goes fast. All right. Profile. Who am I following? Maybe I have to look for lens. Bot of lenses. This is like a little bot somebody put on Twitter. It just every 3 hours tweets a random lens from the book. But I like this one today. For example, this is a curiosity. What am I doing to make the players care about the questions the game gives them? So here's an idea of how can you go back to your game and work on this aspect, for instance, right? Or another one could be, let's see here, chance. What in my game is truly random? What parts just feel random? All right, so there's another element of game design you could work on. Endogenous value. How can I make something even more valuable to players? So these are some deeper questions that you can use to work on the design of your game in a bigger way than just, okay, I just added another feature. All right, but is it working towards some bigger idea? Okay, let's see here. Okay, so that's what I'm looking at for homework number 5. So, feel free to take one of your previous, and then you kind of get more details, I guess. It makes it more deep. You get a little bit better chance of making it better. Okay. All right. So that's due on November. So if you already submitted a homework 5, you can keep working on it. All right. Okay. So that's just a note for homework 5. But let's go ahead and talk about ray tracing. All right. So ray tracing is a very different problem than rasterization. Rasterization, we know where the polygons are, and we can assign the pixels. We can determine which pixels do those triangles belong to. And ray tracing is it's a different approach because what we're doing is we start off with the camera and we want to find out, well, okay, which rays do the pixels go through, or which pixels do the rays go through, and then what happens to those rays, so we can determine what the pixel color ought to be. So we're not so concerned with whether or not a triangle exists there or so on. We're more concerned with what is the color that's supposed to be there. That's the bigger question we're trying to answer. Okay. With rasterization, it's a little backwards. It's more or less, okay, we know something's supposed to be here. Now what color is it supposed to be? And ray tracing is, okay, we know light is coming in this direction. Now what color is that light? So it's a little bit backwards, but you need a few components. So you need an image to store your results in. That's pretty straightforward. That's the same as rasterization. We need a camera. That's also the same as rasterization. We need to know where are the rays coming from. And and we have our objects in the scene and our light sources. Okay, so we know where things are, where the lights are, where's the camera. The difference, though, is just the approach and how we get there. Okay, so there's two kinds of ray tracing. One's called backwards ray tracing. One's called forwards ray tracing. And so can anybody guess what we mean by forwards ray tracing or backwards ray tracing? Exactly. Yeah, one starts at the camera, one starts at the light. Okay, so we call it forward ray tracing if we're tracing the path that the light takes through the scene. Okay, and we call it backwards ray tracing if we start from the camera and go into the scene. All right, so which is probably most likely to be used? Backwards ray tracing is most likely to be used. And that's because it's just like rasterization. We can control, we know where the triangles are. So with backwards ray tracing, we know where the pixels are. So let's start there, because it's possible that if we pick any direction from the light source, it might not get to every pixel. Okay, we might end up sampling some pixels more than others, and so you'll end up getting black areas. This is partially the reason if you ever look at a path traced image, they tend to be very noisy, and that's because they're typically trying to start with the light source or both directions at one time. All right, so for ray tracing in this simple example, we have a few different kinds of rays. One's called a shadow ray, and the other ones are called view rays. And so the idea behind a shadow ray is you first would check if you're finding intersections along the path of the ray. So for instance, the area that's in shadow over here, we would find out, okay, let's cast a shadow ray toward the light source. And if something intersects it before we get there, then we know it's going to be in shadow because something is blocking the way. All right. And in this case over here, we do a shadow ray and we determine, oh, okay, nothing is blocking the light source. So let's go ahead and determine what the shaded color ought to be. Now, the way that we start this process is we have to start from the camera and we have to plot rays through the pixels. Okay, so we generally would pick the center of each pixel as you know, as the direction that the ray should travel in. That way we have good coverage, right? But there are plenty of other, we call them sampling strategies. There are plenty of other strategies we could try. We could try doing random sampling inside the area of the pixel. So we can say, let's not focus on just one area. Let's kind of spread those rays around. Another approach is to use a jittered sample where you kind of divide the pixel into several blocks and you decide where in those little blocks do you send the rays through. And then you sum up, you add up the contribution or average the contribution of all the rays shot through those smaller parts of the pixel, which we would call subpixels. Okay, so this is one strategy. And so you can see our image over here. We have a width and we have a height. And so this would be your resolution over here. So if you're going to shoot rays out, we want to make sure that we're not shooting rays at the corners. We want to make sure we have some, that we know what we're doing here. You can do that. There's nothing wrong with that. But it's important to understand what you're doing, because if you're trying to trace a problem, it's helpful to know, am I tracing rays through the middle of the pixel, or am I tracing rays on the edge of the pixel? What's going on? All right. So anyway, so this is our approach here. And so our camera is going to have some angle theta that says how wide is the field of view. So you have this is what that not the lookup matrix, but the projection matrix is often used, or the perspective matrix is often used to kind of set a percentage or a theta, an angle theta that we're going to kind of open up the lens at. Okay, so a little bit of a back history on ray tracing. Ray tracing was the main work was done in the late 70s by Whitted, Turner Whitted. All right. Now, ray tracing up until that point, so he kind of was doing his work in 1978, 79-ish. The famous paper, I think, was published in 1980. But it was one of those things, and when you look at it, you're like, ray tracing. Okay, that seems like it's a pretty obvious solution, right? We know how to, if you've ever been in a physics class, especially physics 3, and you take an optics part, you kind of know how to trace rays. You say, okay, here's my interface, and if I'm going to do a reflection, then I know I just mirror it around the normal. So if it's bent 30 degrees from the normal, then it's going to be bent 30 degrees going away from on the way out. So reflection is not a difficult problem. So that wasn't a big issue. The problem is that generating, I guess, calculating the reflection in a rasterization thing is hard to do, because then you have to figure out, well, what does the environment look at? So then you have to calculate intersections between objects and rays before you can determine what is the reflected color supposed to be. So it's kind of a expensive operation to compute, because you're not going to just test rays against everything just to get good reflections. So reflections was a problem for rasterization. And even nowadays we would do something like a cube map. We'd actually try and render the scene from the viewpoint of the object that's reflecting, and then we can use that cube map to determine what the reflection color should be. Okay, so the next problem was shadows. So given an object, we're drawing polygons here, what part of the screen is in shadow and what's not. So they have two approaches there. The first one is shadow volumes, which we just took a look at. Shadow volumes, you just kind of project the geometry out and you figure out if you're inside the shadow volume or outside of it. That was kind of invented by Frank Crow. And so that's one approach. And then the other approach is shadow mapping, which is by far the most popular technique, which is let's render the light from, let's render a depth map from the point of view of the light source and determine, when we're looking at from the perspective of the camera, is this area being shadowed or not? All right, so you use a texture map to record depth values from the light source. All right, so that's not a big problem, but you tend to get low resolution shadows, or if you ever played a game and you saw blocky shadows around the edges, that there's a reason why you have to use a high resolution shadow map. Okay, so we have three problems here. We have the reflection problem, we have the shadow problem, and we have the refraction problem. Refraction is the last one, and so that one's probably most difficult because you have to determine, okay, let's bend let's bend our array towards the normal, right, or away from the normal, because you have the index for refraction, and then you have to figure out, okay, now you're in the same boat as reflection, and you're trying to figure out what should the color be. Okay, so these were all expensive things, and so for every individual problem, you had some people working on shadows, you had some people working on refraction, you had some people working on reflection. Now, what Turner Whitted did was say, let's just do all of this at one time. And that's when he invented the ray tracing algorithm. And more or less, this is a good description of it. When he invented it solved all three problems at once, simultaneously. We got shadows, we got transmission, and we got reflection. And so that was the kind of thing. It's like, okay, now we can actually produce a high resolution image. And so, but if it's kind of funny to look at it, because the problem is, why would you waste so many compute cycles? We know how to do this stuff mathematically, but it's expensive. And so what Turner Whitted said, well, if you just do it all at once, then you actually get the image you want. And so that was kind of the aha moment. It was like, oh, okay, let's do everything at once. And all of a sudden you have these really fantastic images that were far better than anything you could generate with the rasterized approach at the time, even if they were very expensive. And so I heard one lecturer kind of joke that the 1980s, all the like extra compute cycles on the supercomputers were basically being used to render spheres. And I thought that was kind of funny. But so I was going to show you this, the complete angler, which is a classic video on kind of showing the original ray traced images that he generated. So this one had texture mapping, it had reflection, it had refraction. And so these were images that you could not produce with any kind of rasterized approach. And even today, you cannot generate images this good without ray tracing. You just need ray tracing, or you're going to spend a lot of extra time trying to get there. Okay, so this handles reflection and shadows and the whole 9 yards. This guy, in fact, was the guy UC Davis was talking about the history on the whole ray tracing algorithm. Okay, so we have the complete angler, and so Turner Whitted kind of changes the approach to computer graphics. So ray tracing would still be very expensive for a very long time, but it kind of paved the way to path tracing and some of the more heavier duty approaches to the ray tracing problem. Okay. Now, so this is something to remember, that the rasterization problems it solves: shadows, reflection, and refraction. Those are the three problems that he solved simultaneously. Okay. Now, ray tracing has its problems, though. Okay. One of which, all right, we can almost see from this point of view. All right, maybe not entirely, but the problem with ray tracing, and this is not a problem necessarily with rasterization, right? You do rasterization, you're drawing triangle, 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 and with the Z-buffer algorithm, if you can more or less get that right, you don't have very much overdraw. And so every pixel gets evaluated approximately once for rendering purposes. Okay, you basically just throw out the ones that you can't see, but for the most part, every pixel is probably log n at least, if not shorter than that. Okay, you're trying to search for the closest pixel. So I would guesstimate that in the ideal case, a rasterized render is 0.1, because you only draw the one polygon, and probably at worst case log n, because of if you can more or less sort the polygons front to back, then you have very little overdraw. Okay, that's just my rough guess of what it is. Now, unless worst case scenario, you had all the triangles right in front of each other, sorted back to front. That would be ON, but that's not likely to happen. So So if you have n triangles in your scene, you're a lot closer to O1 or O log n time to render each pixel. Now let's see what happens with ray tracing, okay? And let's just take, we'll take one of these rays and we're gonna hit this first object, okay? So we have n objects in the scene and we take this first ray, and so that's O1, right? That's one single step, but you have n objects in the scene. So you have to test your ray against n objects. So this one pixel, you know, we have to do n comparisons, but then we're going to generate 3 rays. We generate 3 rays. One is a shadow ray to the light source. One is a reflection ray, so around the normal. And the third one is a refraction ray, which is through the object. So minimally speaking, at this junction, we have 1 ray, it hits an object, and we generate 3 rays. Okay, so what's going to happen to each of those 3 rays? Let's talk about the shadow ray. What happens to the shadow ray?
The shadow ray has to check every object in the scene again to see if it impacts any of them on its way to light.
Yes.
The reflection ray has to check every scene in the object again to see what object it hits next, which could then generate another set of 3 rays. And the refraction ray,
It's the same boat.
It's check the same object again, but then it could exit.
It can exit, but I guess what's going to happen with this? What happens to those rays after that?
A lot more.
So what ends up happening is you get this growth of rays that you're checking against. So it's not just like I can send a line of rays and get my answer. I have to send a ray that keeps multiplying. So what happens to that kind of growth in computer science? It can grow exponentially, and therefore an image with, say, m by n pixels can take exponential amounts of time to produce. That's why path tracing or ray tracing is so expensive. So the only way, so basically that was the big problem then. Okay, Turner Whitted says, well, just try ray tracing, just try all these approaches, it's going to solve all your problems. And that sounds like a nice checklist. Yes, we got shadows, we got reflections, we got refraction, but the problem is each ray then triples every single time it hits something. A worst case, and so that then became the source of the next, okay, now we would like to fix, what happens if we approximate this, like we don't let the recursion go so deep, or but you do get some issues. So a lot of the work in the 80s was then trying to determine what can we do what can be better than path tracing, okay, or than ray tracing that also gets us the same effect, okay? So the next, one of the approaches that was tried is called radiosity. And so radiosity is actually a different approach than ray tracing. I would say radiosity is not as popular as it used to be. But the idea behind radiosity, and you can see in this, inside this screenshot here, maybe I'll just dim the lights just a hair. With radiosity, you tend to get results that you get those soft shadows like you would expect. This would never look this way in a regular rasterized. You'd have flat, more or less flat shaded walls, and you wouldn't get soft shadows. And so this was actually a remarkable improvement over ray tracing, because most of what you see, even if you look inside this room, it's very rare to see even a sharp shadow anywhere inside the room, okay? The only time you get sharp shadows is when you have a really bright light on the edge of an object, okay? So the ThinkPad over here has got some sharp edges, and we have a bright light over here, and so it's, yeah. So, and it's about as close as you're gonna get to a sharp edge shadow in here, all right? Most of the shadows are soft. They do, yeah. So if you have a point light source, those tend to produce sharp shadows, but what if you have an area light source? So an area light source is even more complicated to produce in ray tracing, because the example here is that the light source is like a point light source, or it's directional, it's only coming from one direction. So if you want to model more sophisticated lights, it's very difficult to do with ray tracing unless you just increase the amount of samples that you're willing to take, okay? So So here's how Radiosity works. What Radiosity does is we use this idea, it's called a form factor. And a form factor says, okay, we're going to solve this hemisphere problem that we've looked at before. And we're going to say, if my point that I'm interested in shading is in view of a little patch in the scene. So we're going to basically take the scene and chop it up into smaller and smaller pieces. And we're going to project those pieces onto this hemisphere and determine how much light is actually reflected from this little patch somewhere in the scene on the surface area of the table or whatever I'm drawing, okay? And so, so you have this projection problem. So if you can tell, it's very difficult to have an arbitrarily shaped surface that you can then map to this projection here. So there's a few closed form solutions for like square patches and so on that people have worked out that'll say, here's the exact contribution that this patch of light will provide to this other surface. Okay, but the idea here is that you would then compare every other patch or form factor to every other patch or form factor inside the scene. So Radiosity becomes very impractical as soon as you start to increase the number of patches inside the scene. So one very famous approach to using Radiosity in real time is called light mapping. Who's heard of light mapping before? Heard the term. Okay, so light mapping is actually still very popular. And if I were to search for light mapping, this is hopefully we get a computer graphics version of light mapping. I'll just type in Quake. There we go. So here's a Quake light map, all right? And so the idea here is that you would just divide, you would set the texture maps and then you'd calculate the amount of light that's reflected everywhere. So this will get you that soft lighting, but you can do it in real time because these are just texture maps and the texture map can then modulate the texture color, all right? So that's, I guess, linear texture maps there. Well, that's the thing though, is you have to pre-render the light map. So you calculate the light map in advance. And then let's see if he has other images for this. So there we go. So there's the diffuse, so no lighting at all. And then you have the light map. And so if you're going to apply the light map, you could also use bilinear filtering for the light map, all right? So you get the smooth version. And hopefully there's the finished result. So you get this natural lighting effect that looks like Radiosity, but can be done in real time. The problem is you can't just turn lights on and off or move them around if you want to because you can't recalculate it. So light maps are basically storing a pre-calculated solution, and then you can just draw the light map when you're drawing the object. Okay, so there's so that's part of the Radiosity problem. So let's take a look at this. So if you had two scenes over here, we have the scene on the left is direct illumination, so you can see sharp shadows. This would almost be like applying the Stencil Shadow technique, so you have perfect shadow volumes. And with Radiosity, we can actually get that soft shadow effect, although you will quickly observe, maybe not in this image, but you quickly observe that when you're dealing with Radiosity, they tend to have these like edges because we're dividing everything into squares. So here's an example here of and then it's also an iterative approach as well. So what we'll do is the first time around, we will say, okay, only the patches that are in direct view of the light source will get illuminated, okay? And everything else is black because everything else was black before, right? So the first pass, only the form factors that have light on them get any reflection. The second pass is a pretty big deal because now you can take all of these other patches and they can now be exposed to the light on these patches over here, okay? So for this patch, we're actually checking every other patch inside the scene and determining visibility to it. All right. So third pass. So once you get the third pass, it's starting to look pretty close to the final result. Okay. pretty close. You're always going to have, you know, so every pass that you do, you're going to get less return, you know, back. Okay, because there's less light being reflected. So the idea is to just, you know, you'd let it soak until it says, well, the difference between this pass and the pass plus one is less than some epsilon value. Okay, so it's basically a numerical integration technique where you can kind of like build it up over time, and then you can just say, we'll stop right here. So this is actually how light maps are generated. These squares actually would correspond to pixels inside the texture map. And then you can just apply the texture map at runtime without having to recalculate this. But if you were to move the light source, then you still have the same problem of got to recalculate everything in the scene. But it looks good, all right? So, I mean, clearly, you know, given this versus a normal rasterized image, this looks far better than what you get. Although you'll notice that there are some issues with light leakage around corners, all right? So over here, we have an issue here with light leakage. And so if you don't define the subdivisions in your geometry appropriately, then it's possible that you end up getting errors inside your final result. And this is a problem that applies to many different kinds of global illumination techniques. Okay, so I thought we could take some time to take a look at Disney's Practical Guide to Path Tracing, because path tracing is kind of the if you want to know state of the art, path tracing is state of the art. So this is a 10-minute video. So let's go ahead and watch this and kind of get an overview. I guess, I don't know if Disney uses this to teach their own people about how path tracing works. I'm guessing the artists, but this will probably give you some handy, you know, how do you talk about this to other people? All right, so let's go ahead and watch this video real quick. And learn from Disney.
There are roughly 100,000 single frames that make up an animated motion picture. Hundreds of artists will work their fingers to the bone to bring just one image to the screen. Right now, we want to share with you how one of those images is made. Sounds simple, right? Just one frame? Well, think again. First, we'd like to clear all imagery from the screen. Like a blank sheet of paper, the frame is empty. There's nothing to work from in this frame. Let's start with a frame where you can see it. Just imagine this frame as a window in your home, but cleaner. Outside, you see the hills on the horizon. You see the water, the river, the rocks, and the trees. And you see the sun above. We all know the sun has light beams radiating from it. They travel down, down, down until they hit objects here on Earth. Like this rock here, making it visible. The rock does not absorb all of that light. It actually interacts with it. And this type of interaction depends on what that rock is made of and what its surface texture looks like that determines where that light goes. The rock surface may be smooth and reflective, like a brand new shiny car, which will cause that sun ray to bounce off of it, casting light on the backside of this tree. But the light doesn't stop there, folks. It may bounce off the bark surface and head into the leaves, causing them to light up a little bit too. Then bounce again and again, like a billiard ball at a pool table, until that single ray of sunlight has finally lost all of its energy. We begin to notice that the sun does not light all of our trees and rocks directly, but rather through indirect paths like this one. Most of our shady spots are not black darkness, but mostly visible because light found its way in there. That was just an example of what happens with a single ray of light. Just imagine this for every ray of the sun. There must be millions, billions, bazillions. There are infinite paths that light can take, illuminating everything we see. That is a lot of light bouncing around. That's how physics works in the real world. But what about animated movies? Let's look at how the computer does it. Imagine the window as your computer monitor looking out onto a virtual scene. All objects in the scene, or world, are 3D models. They are represented here as wireframe objects. This is how they appear to the computer. It is our job to paint them with texture. Let's take a closer look at that rock underneath the tree. When creating this scene, we are able to art direct this rock's surface and therefore how the light will bounce off of it. Will this stone be smooth like a pebble, which would cause the light hitting it to bounce back cleanly, uniformly? Or should we make the stone's surface jagged and jumbled, creating more unpredictable behavior on how the light might bounce? This is all known as surface appearance. Every object in the scene has its own art-directed surface that dictates how it interacts with light. But that does not determine how the object itself will look. If this rock is smooth, is it a smooth rock made out of marble? Or maybe granite? We can art direct this rock and pick which one we want. We can be creative. Now we have a beautiful granite rock living under our tree with a smooth, reflective surface. The process for building this image inside the computer is called rendering. The computer has to make a calculation for every ray we see, adding up to billions and billions of calculations in a scene. These calculations take time, and often demand more than what the computer is capable of. So how do we get around this issue and keep the ray count down to just what we need for what is computed? In our scene, every time a light ray bounces from object to object, the computer needs to calculate its new trajectory, its direction. Some rays may hit that rock first, others go into the river. Some travel into the sky, where we'll never have a chance to see them. So what is the point of calculating those rays when they'll never be in frame? In order to produce a more efficient render, we use a method called path tracing. This method reverses the process and considers only the light paths that are visible to the camera. Path tracing involves emitting rays from the camera, tracing them back to the objects in the scene and then back to the light source. That way, every single relevant ray of light is accounted for without wasting time tracing paths of light we'll never see. Wow. I know what you're thinking. How can we be even more efficient? Well, in order to answer that, we need to understand how the computer works. Every time we tell our computer to create a camera ray, it has to do a calculation, a task. For example, we ask it to travel outward from the camera and hit that rock. That's one. The rock's surface appearance then tells that ray how it is supposed to act. The rock is reflected, so our computer will now begin a new calculation, plotting our ray's next direction. That's two. It will encounter another object, 3, then another, 4, eventually tracing its way back to the light. The way our computer processes these tasks is using a, processor. It takes each ray or surface hit and calculates it for us. And it may do this millions or even billions of times for every image we make. You can see the computer has a lot of work to do. Camera rays don't emit one at a time. Instead, millions of rays are emitted across the entire camera frame. The first set of rays go out into the scene and capture everything that the lens can see. But one ray hit is not good enough. Again, we have to do multiple hits to make things look natural. Shadows, translucency, everything seen in the real world. A ray may need about 4, 5, maybe even 10 times or more to create the look we desire. Once our rays leave the camera and scatter through the scene, things get complicated. Our computer wants to render these rays evenly and uniformly, but there is no inherent ray organization. At random, it tries to grab each single ray, place it on the processor, and try to render it. This is like doing a single problem from your math homework, then putting your book away and pulling out your history book, only to write one sentence for your history report. I don't know, probably about some king that nobody's ever heard of. Then, after finishing that one sentence, close your history book and pull out your math book again to solve just one more problem. This is crazy! Just stop. That's not a good strategy for doing your homework. It'll take you all night. Computers work in a similar manner. It doesn't matter if one ray is headed toward the river or the next ray is heading into those bushes. It doesn't know any other method to render those rays. It's better to do 10 math problems at a time or knock out a paragraph or two from your history report. With computers, you can organize certain rays by telling them to batch or bundled together based on where they're traveling in a scene, their direction. Because some rays are traveling in the same direction and have similar characteristics, we can batch them together and place them on the processor to be calculated at the same time. See those rays there? They're traveling in a similar direction. Let's bundle them together. Let's also group those rays heading toward that part of the scene. And so on and so forth until we have rendered the entire second batch with the processor. This is called ray sorting, and this is our method for path trace rendering. Pretty nifty, huh? We repeat this sorting process for the third, fourth, fifth bouncers, as many as are required until our scene is ready how we design. By grouping similar tasks together, we are able to trace many more rays in the same amount of time. It is more efficient because it reduces the overhead of switching between different kinds of tasks. Hence, it allows our scenes to render faster and lets our artists create more detailed and beautiful images. In summary, using these three methods, we can build our scene. Surface appearance, how light will interact with the object, painting the look of the object, and organizing rays of light to make our scene visible. To create our worlds and bring them to life using the physics of light.
I thought that was amusing to watch because it kind of refreshes everything that kind of goes into generating an image. So they use a word called indirect, all right, indirect lighting. And so more or less when we're rendering objects, you have two kinds of paths of light. You have direct illumination and you have indirect illumination. So direct illumination basically is those paths of light that are going straight from the light source to the object and then to our eye. So that's direct illumination. And indirect illumination is anytime you have a light path that's bouncing around and can take more than one path to get to you. All right. And so that's the biggest, as we saw here, the biggest loss of energy is all that indirect light that's reflecting back and forth. I think Radiosity points that out pretty well. So this would be direct illumination, just that first path, and indirect illumination then is accumulating all of the other passes of light. All right. So before I talk about real-time ray tracing, I want to show you a paper. It's a pretty good paper. Well, it's a dissertation, and which was robust Monte Carlo methods for light transport simulation. And so what Eric Veach kind of did here is just kind of summarize different approaches to this. Now, this kind of got started with back in 1986. So we saw the rendering equation by who? Kajia. Okay, so Kajia kind of brings the path tracing. And what Kajia did essentially was he went and he was doing research on statistical methods. And he recognized, or he was a number of researchers that recognized that all the work that was done in the 1940s to simulate the atomic bomb could be used for ray tracing as well. So that all kind of falls into the neutron transport theory. So if I were to go to Amazon and search for neutron transport, that's funny. No, I actually have let's see if I can find the book. I have this book on my bookshelf. It's a green book. Oh, what's it called? Maybe it's called Neutron Transport. Let's go over here. Let's see if he has his bibliography. Nope, that's not gonna work. Okay, the other approach. Let's go. File, open. There we go, Spanier and Gilbard. So this was the book that I read that introduced me to neutron transport problems. Oh, I guess that was the book. Okay, that's cool. That's hardcover, but paperback's only $12 because it's one of Dover prints, right? So the cool thing about this is that, you know, it's going to teach you how to do Monte Carlo integration, but they kind of give the theory behind it, and there's some fun stuff that you can learn from here. 1969, and the idea here is, let's see here. I think that I've read the first 3 chapters, and then it starts to get harder because these are physicists, right? And so the physicists have really spent some time contemplating all this stuff. But what Kajiya was doing is kind of like, okay, neutron transport, which is the idea is, where do all the neutrons go? If you're trying to simulate what happens when 2 atoms are going to, you know, ram into each other, where do the neutrons go? And so use the same statistical ideas with light, because we're trying to figure out, where do the photons go? Because they're bouncing around in the same way we expect neutrons to bounce around. So all this work that was done in the 40s, because I mean, you have to think, how do we know what an atomic bomb is going to do? It's not like we're going to experiment with this in the laboratory, right? I mean, theoretically, the numbers are big. You know, they're like, this is a lot of energy. So, and if you've ever seen a video of the atomic bomb, you know that is a lot of energy being released with a very small amount of material. So what they would do instead is they use the idea of Monte Carlo, which is does anybody know what Monte Carlo is? Monte Carlo, like the car. More specifically, it's the place in Europe. Monte Carlo is a place in Europe on the French Riviera. And what do you think Monte Carlo is famous for?
Rich people.
What else? Gambling. It's the gambling center, which has made Monte Carlo an international byword for the extravagant display and reckless dispersal of wealth. Okay, so Monte Carlo, this is where we get the, you know, when you see Monte Carlo integration, it's because it's named after this very famous gambling place where you just throw your money around, all right, and we'll see what happens. So Monte Carlo, oops, let's go back over here. So this is how you do it. So instead of trying to sample all of the problem, just solve smaller bits of the problem, and then we'll see what happens. Okay, so for instance, one of the simplest ways of doing Monte Carlo is to estimate the value of pi. Okay, so if I were to search Monte Carlo and pi, the idea here is that you could just throw a bunch of random dots on a grid. All right, let me just find, where's the image? Just grab an image here. Here we go. So the idea here is that you could just plot a bunch of random points on, on a quadrant, and then you can test to see, well, how many of these points are inside the circle and how many points are outside the circle. And there's an easy test for determining that. And that's just to check x squared plus y squared. And we know that if it equals 1, it's on the circle. But if it's less than 1, it's inside the circle. And if it's greater than 1, then it's outside the circle, right? Because the radius of a circle, right, anything underneath the radius is going to be less than 1. So then you can measure the ratio of points that are inside of the circle versus the points that are outside the circle. And by doing this, then you can estimate the value of pi. So this is an example of how you use Monte Carlo to estimate the value of a function. So you don't know the value of the function, but the idea here is that if you throw enough darts, you end up getting the picture or the solution, right? One kind of classic example is if you throw enough darts, then you get the Mona Lisa. That's kind of a joke, right? So, but the idea here is, okay, let's not try to solve the entire problem. Let's go ahead and just try and solve parts of the problem. And Monte Carlo, when applied to computer graphics, is the same way. We mentioned the hemisphere. So instead of sampling the entire hemisphere, like actually calculate an integral, what we could do is we could send out a few feelers and find out, is this brightly lit or is this not brightly lit? Okay, so Veach is, so we have Kajia introducing the rendering equation and Monte Carlo to computer graphics, but we also have Eric Veach is doing some work here on his dissertation. And one of the things that he did, and this is actually a really good thesis if you want to figure out or get some inspiration on how you should do it. I used it to kind of help inspire me. But let's see here. I'm looking for path integral formulation. Okay. I don't want PostScript. PDF. Let's see here. We'll just look at this one. Okay, it's the power of LaTeX. You can print these huge books if you want to. Okay, so I'm gonna skip down here because he's got some good figures, all right, and a whole bunch of math. And this is why, yeah, this is the one I want. Bidirectional path tracing. This is probably the most popular algorithm out there for doing path tracing. This and other variations on this one, because what bidirectional path tracing does is, first we want to express light transport as an integration problem, so which is what it is. And then two, one of the ways that we can do that is, we mentioned shooting, you get some inefficiency when you shoot rays from the light source. Namely, you don't get all of it takes forever to get an image. And the other problem is that if you shoot it just from the camera, then you're not guaranteed to get all the light samples that are interesting, because shadow rays is not exactly an accurate way of determining what light is in the scene. You need to, because if you had a mirror and you don't sample the mirror and you have a light reflecting on the mirror, you're missing a huge area of where all the light is going. So the idea here is that, let me find one of his, is that you can approach the problem from both sides simultaneously. So we'll shoot rays from the light source and we'll shoot rays from the camera. And the idea here is at some point, you're going to just take the two pieces. So maybe you have a few reflected rays from the light source and you have a few reflected rays from the camera, and then you'll just connect the dots and you'll just say, okay, let's put those two paths together and let's figure out how much of that original light path is going to be visible from the camera. So it's a way of, instead of saying, because if you just let it go forever, you could end up having light paths that don't go anywhere. So at some point you got to decide where's the light going to go from. Okay, so we have bidirectional. Okay, so you could start simple, right? You could just say maximum length of, say, 1. So you only have one length from the light, one length from the camera. And, that'll get you a certain amount of indirect light, but you can let it go for longer if you want to kind of deep sample the image, if you will. Okay, so let's see if he has some, one of the big things that bidirectional path tracing was useful on was, let's find it. Let's go. Was sampling refraction rays. So let me zoom up over here. So if we can see over here, if you do bidirectional path tracing, in other words, you're connecting the dots from both sides, then your ability to, with 25 samples, we're able to get an image that looks this good. Whereas if you use 56 samples, the same amount of time as the previous method of just start from the camera and just keep going until maybe you hit the light. That's why you have all these speckles here. We call them fireflies. And that's because we just don't hit the light very often. All right, it's just accidental. Whereas we start both ways, then it's more likely that we will get those directions. Okay. Here's another approach. Let's see what this one is. Weighted contribution. All right. There's one other image I'm really looking for, and that's, he has one where it's showing reflection. Metropolis is another interesting approach. What this does is takes those long light paths and it'll use genetic algorithms essentially to mutate them. So we try to figure out, can we find some light paths that are doing very well for us? And if so, let's go ahead and concentrate our sampling around there. So there's mutation. And let's see if I can find, this is kind of the idea here, is with mutation here, if I know I'm getting a bright, like we're looking at caustics, if I know I'm getting a bright area, let's just change that a little bit. Rather than compute a completely random path, let's use a random path that looks pretty good already and keep going there. So that's one strategy of Monte Carlo. Let's see here. So this is kind of cool. It's kind of like one of those as seen on TV, but wait, it gets better. So this is bidirectional path tracing with 40 samples per pixel, and then by adding the random perturbations, 250 mutations per pixel, so same computation time, and now all of a sudden you have an image that converges way quicker. Okay, so we're kind of getting an idea here that the path tracing, or if you compare this path tracing with the original one, there is definitely a lot of room for improvement there. Okay, this is kind of showing an up close detail of these caustics that are generated by this egg shape. All right, and that's with Metropolis light transport versus bidirectional path tracing. So bidirectional path tracing already looked good. Metropolis made it even better. Okay, so here's and when you look at this, basically this is something that would be almost incomputable, with regular ray tracing or path tracing. Okay, so power of path tracing here is that by using some more advanced methods, we can approximate. Okay, approximate our scene. Okay, so that's one of the reasons why I think his dissertation is exceptionally good. I mean, it is an extremely well-written project. And so done in 1997. So you can just imagine, and he's got some I guess it helps that you have James Arvo and Pat Hanrahan and some of these other folks. Guibas is also done a lot of great stuff too. Okay, let me see if there's that's probably enough for that. I wanted to start getting into the real-time ray tracing though, because that's what's happening nowadays, right? So just by way of, so we can kind of see the power of ray tracing, let's just watch real-time ray tracing demo. And I think the one I want to test, this is 6 months ago. Let's watch this one. Unreal Engine is probably the most popular version of, the most advanced engine out there that will do ray tracing.
4.22 continues to push the boundaries of photorealism in real-time environments, whether you're making immersive and engaging games, broadcasting live television, visualizing groundbreaking products, working on a blockbuster film, or creating an interactive experience of the next landmark building. With new hybrid ray tracing, Unreal Engine offers the quality and ease of use you strive for without the time cost of full ray tracing. Using an NVIDIA RTX graphics card, reflections, soft area shadows, translucency, ambient occlusion, skylights, image-based lighting, and global illumination can now be ray traced, while other passes continue to be rasterized. By opting to ray trace certain passes, you can avoid time-consuming and difficult workarounds, such as reflection probes or planes. Ray tracing allows you to achieve more subtle and accurate effects, such as soft shadows from area light, or illumination from a skylight with HDR textures that contribute to the realism of your scene. Here, we're using a post-process volume to toggle on and off the ray trace passes for reflections, translucency, and soft ray trace shadows, providing the finishing touches to ground your scenes firmly in reality. As you can see, by selectively ray tracing just the passes that benefit from it, delivers greatly accelerated results over non-hybrid solutions. In addition to the ray tracer, we've included an unbiased path tracer with a full global illumination path for indirect lighting that creates a ground truth reference render right inside the engine. This enables you to validate the results of the hybrid ray tracer without needing to export to a third-party offline path tracer for comparison. With its ray tracing capabilities, Unreal Engine 4.22 delivers unbridled power to build realistic worlds with the most accurate real-time lighting and shadowing effects.
Pretty cool. If you add sparkly sound effects to your demo, it'll make it feel more real as well. Okay, so so real-time ray tracing is one of those, you know, it is here. Okay, and so in the coming years, and especially as the next consoles come out, it's going to be all over the place. Now, the realistic thing, you know, we saw those really nice images that Veach generated, you know, 25 samples per pixel or even more than that. It's not uncommon to send hundreds or thousands of samples per pixel in order to get a really high quality render. Now, real-time ray tracing, when they throw, it looks good, but you have to realize that they're doing 1 to 2 samples per pixel. And that is a, you know, if you're just to take the raw output there, it takes a lot of denoising to kind of figure out what's going on. So there's, you know, no doubt in my mind that it'll continue to get better, but it's still kind of in its infancy. And then you also need, like, you know, an expensive graphics card to do that. So one thing that we want to do is learn real quickly how the real-time ray tracing works. Okay, so let me pull this back up. So the idea here is that the pipeline has 6 different components associated with it. All right. So the first component is ray generation. All right. This is something that you're going to have to remember. We have ray generation. So this is we have this payload that we will kind of initialize that's going to go along for the ride. So each of these shaders have access to the payload. So you'd set things like material properties or different aspects to that. And that's just some common information that ray will need all the way along its path. So in the ray generation, the whole idea here is that we want to initialize the payload and generate the rays. Okay, so the next part here is an acceleration structure. So let me go over here and just kind of show you the high-end view. So we have ray generation. It's going to trace the rays, initialize the payload, and then we need to go through this acceleration structure in order to determine, you know, the fastest way to, you know, we said if you're going to do rays, you got to test the rays against every single object. Well, that's not efficient. So there are methods of sorting those so that you only have a handful of objects to detect collision with. So in order to do that, we go through this acceleration structure. And if necessary, we'll call it intersection shader. So if your polygons, I mean, if your object's just made out of triangles, then the built-in real-time ray tracing will automatically do triangles for you. And we'll check for an intersection. And if we find an intersection, right? And so the intersection shader, just real quick, is for procedural objects. So you can say, let's do a sphere, or let's do something else that's, you know, not simple, like procedural model, for instance. But once we've found an intersection, then we'll just call it any hit shader. So a lot of these components are actually optional. You just turn them on for whatever that you need it for. But, you know, an any hit shader is something that would be useful for shadows, for instance. So if you're just trying to see, you know, check to see for this particular, you might set the payload to say this is now shadow rays. So you might say any hit. Yep, we got one. Let's go ahead and kill this this ray. This is a shadow. And so the any hit shader, you go through this as we're going to this acceleration structure. We'll call the intersection shader to determine whether there was an intersection, and we'll call any hit if it was hit. All right. So once we've got through the acceleration structure, we have one question that we need to ask: was there a hit? Okay. And so it can either go one or two ways. The first one is, yeah, we did get a hit. So we have what's called a closest hit shader. And this is probably our most expensive part. Is, you know, this is where we do the reflection, calculate Fresnel, use our microfacet, BRDF, and so on. And so yeah, if we got a hit, then we can apply the closest hit shader. So we do all the reflection, and these in turn can actually call trace ray again and recursively generate more rays. Okay, so you can set a maximum ray depth if you need to kind of control how deep that will be allowed to go. Otherwise, if you don't have a hit, then we can do a miss shader. And so you can use this as an opportunity to say, well, if we miss, that means we're outside the scene somewhere. So let's just grab the color of the sky or an environment map or something, or just return black. And so we have these 6 components here, right? So ray generation. So this is where we generate rays. The acceleration structure is used to quickly test for ray intersections. Then the intersection shader is, we can use that for procedural objects, otherwise we just test against triangles. The any hit shader is good for checking to see if anything hit. This is also good for participating media. So maybe you're trying to do volume or like fogs or volumetric effects. So they don't really correspond to like a geometrical object, but you can say, okay, let's see how far we get to this volume before we reflect light from outside or something. And then the closest hit shader gets called after the any hit shaders. And like I said, this is recursive, and you often get the barycentric coordinates of the triangle. So this is where inside the triangle that you hit. We'll talk about barycentric coordinates in a future date, but this is a useful way of representing where you hit inside of a triangle. And then the miss shader, like I said, is what happens if you don't find a hit. So let's see here. This is where I want to talk about the homework assignments for 6, 7, and 8, although I'll zone in a little bit more on 6. So there's 3 books that Peter Shirley wrote, Ray Tracing in 1 weekend, Ray Tracing the next week, and Ray Tracing the rest of your life. So we're only going to focus our efforts on ray tracing in 1 weekend and a little bit on the next week, but mostly the 1 weekend one. We'll see how far we get. The way that the books are organized is that the first one is about writing a brute force path tracer. Okay, so this is the simplest one that we can write, and we're just going to work on spheres. I showed you an image before what that looked like. Looks pretty good. And then the second book focuses on more advanced things like texture maps, volume, like fog, and so on, rectangles, instances, a lot more items. So these are all the advanced type things that you really will make your image look pretty cool. And then the last book is the math behind a serious ray tracer. So he tries to give you an introduction to path tracing and the Monte Carlo approach to everything. But for our cases, we just want to work through the material in the first book, Ray Tracing in 1 weekend. So this is if you click on this link here, and I'll have these slides up here, I'll post them after class. But the idea here is that you can read the book, and he's going to talk about a few different things, like how do you generate images, what do you need in a vector class. And so by the end of the book, we're ray tracing spheres, calculating reflection angles, and so on. So by the end of the book, sorry if it's messing your eyes up a little bit, didn't mean to do that. But by the end of the book, you're able to generate a lot of cool looking spheres, I guess. So we get to kind of go back forward to the 1980s, if you will, but in a modern way. All right. So this has actually been a very well-received book, I think, by the graphics community. Although it does have a disadvantage, and that is it doesn't use the doesn't use this programmable shader kind of architecture that is being used with the RTX stuff. So one thing you may consider is how can I, if you read the book a few times, and how can I maybe approximate that structure with my own code? Because there's a lot of downsides to the way that this book does. Namely, we start from one corner of the image and work our way down to the bottom right, whereas a lot of path tracers will subdivide that work. So it's very single threaded, and you could definitely get some advantage by separating out the cores that you use. The process that is done with the first book, generally we learn how to output an image in PPM format. This is a great way of just getting graphics out. You can use like IrfanView or something to view them straight from Windows. And so what do you need in a Vector 3 class? So we're going to kind of break these into 3 parts and focus on implementing them. So with homework 6, there's 3 output images that you need to be able to do. So the first one is, okay, first of all, let's make a PPM image, but we want to make sure that we're able to draw the texture coordinates. So we start off at 0, we end up with 1. So this image should approximately go from black to green in the upper left corner, red in the upper right, and yellow in the upper lower right is red, upper right is yellow. So this will make sure that we're kind of generating the right kind of image. The second image is to make sure we're generating camera rays appropriately. This will, so it should look like upper left should look green, lower right should look orange. And then the last part is a mist shader. So Peter Shirley has this nice little trick to kind of mix between white and blue. And I came up with a little trick to mix between orange and blue. And you can kind of get like a, dawn kind of thing. I think it's a great way to test something different than just blue. Okay. Now, these are actually not hard to do. So if you were going to write like a mist shader, then you would basically just say, let's take a look at the direction for the ray. So a ray is going to have an origin and a direction. And so we can kind of calculate where up in the sky that our ray basically landed. So we're just modeling like a cylindrical sky model. Very simple and not physically based at all. Okay, but we'll just, we use the LERP, which is linear interpolation. So we can pass in a parameter t, which is 0 to 1, and then we can mix the two colors together. Okay, there's really nothing fancy here. And so the colors I used here is white, sky blue, and orange. So there's some colors there. So the first assignment is basically how do we generate some basic images here. Now, if you want to, instead of writing this in C++, I would also recommend you could do it in ShaderToy, which then you're using the power of your GPU and not just a CPU. Okay, so this is one way to do it. And then for homework 7, so this one would be due a week after, on the 10th of November. So this gives you time to read the book and start working on it. And then homework 7 would be due the following week. So we're going to add intersection with a sphere, surface normals, and some simple kind of scene graphs so we can put more than one object in the scene. And then lastly, for homework 8, have a camera that you can move around and use position, add different kinds of materials like diffuse materials or dielectrics or metals, and then add texture maps. So texture maps wasn't in the original book, but I think it's nice to put that in there because you can then add, you can make things look like marble or whatever the case is. Okay, so we'll talk about details later, but I'm going to be adding those details to these slides. So just keep that in mind when you look at the homework assignment. Okay, so to finish up, I was going to show you how easy it is to kind of, how many people have used ShaderToy so far? Okay, it's, yeah, it's pretty, I like it a lot. And so I actually implemented, I was working on implementing this so I can click on the screen. I can either get the blue or the sky version. And so let me see if I hit extra large. I have a different way of approaching writing shaders and stuff, trying to make it like I'm writing a program. I got some color constants I'm using. There's my ray. So I have an origin and a direction. Payload, I'm going to fill that in as I determine what I need to keep track of on the ray. And some of these are just like constructors, so create a ray or create a camera ray. We're going to spend some time next week talking about how do you create a camera ray, all right? Because this is going to allow us to change like the angle that we're able to do. And the idea here is that, the algorithm is like, okay, ray trace the pixel, right? Which is getting that 0 to 1. So which pixel? And then ray trace will just create a camera ray. And then we got to trace the ray through the scene. Otherwise, we just return a mist shader. So at this point, it's super simple, but I can also debug whether or not, let's see here. If I go here, so if I wanted to, I could return the ray direction. And so this gets me that one image. So you can just make sure that everything is operating correctly. Okay. All right. So, and when you're all done, let me hit leave here. I guess I got to sign in. I'll just show you this last. I'm kind of working on getting a ray tracer to work in shader to a way that it kind of closely approximates. But you know, I'm able to do some things like polygons and some more advanced shapes here. So that's kind of what I'm kind of working on. How do I do this, like with just a GLSL shader? But this is going to be way faster than just generating it with your CPU. I can tell you that, because I've already done the basic path tracer he's done in C++, and it's significantly slower than that. So I think it's better to do it in GLSL, get you some shader experience. But it is going to be harder because you have to translate that in your head. So in the past, I've had students do it in Python and C++, just because they wanted the challenge to do it in those. It's all good. So we're really mostly focused on the images that we're generating. And yeah, so I think that's it for right now. So we're going to take a little journey on doing ray tracing and so on. Okay, so I'm going to stop the stream here real quick, and you know, I think we're done. So, but if anybody had any oh, I need to pause that. End meeting.